In the last video, I introduced the method of proof by induction, and we used the example of the sum of the first n natural numbers. Now, in this video, I want to look at this example, which is the sum of the squares of the first n natural numbers. And we want to prove by induction that that sum, that is 1 squared plus 2 squared plus 3 squared as far as n squared, can be gotten by this formula here. We multiply n, that's the nth term, by n+1 by 2n+1 all over 6. Now I proved this result by another method in the sequences and series playlist. Another way to write this sum here is sigma r squared r equals 1 to n. So if you know something about series, you might be familiar with this notation. If you haven't seen it before, it doesn't matter. It just means we start with r equals 1. We plug 1 in for r here and we get 1 squared. Then we increase r by 1 to get 2. We plug 2 in for r here, we get 2 squared. Increase r by 1 again, we get 3, so we have 3 squared. And keep going until we get to r equals n. So the final term will be n squared. The first step in proof by induction, as you saw in the previous video, is to prove that our statement is true for the smallest value of n that is relevant to this, and that value is 1. So let's look at the left hand side when n equals 1. When n equals 1, we're getting the sum of the first one term of this series. We can't even say it really. It doesn't even make much sense to talk about summing just one term, because the sum of the first term is actually just the first term. It's just 1 squared. If we're asking for the sum of the first two terms, it would be 1 squared plus 2 squared. But since we have to prove this for n equals 1, we have to show that it's valid just for the sum of just the first term of the series. So the left hand side will be 1 squared, which is 1. Now let's look at the right hand side. Let's plug 1 into this. So we get 1 times 1 plus 1 times 2 plus 1, which is 2 plus 1 all over 6. So we have 1 times 2 times 3. So we have 2 times 3 divided by 6. That's 6 divided by 6, which is 1. So we get the same result on both sides. So that shows that this formula is valid for n equals 1. Step 2 in the method of proof by induction is to assume that this statement here, so when I say assume true, I'm referring to this statement here, of course. We assume it's true for n equals k. So k is some natural number that is greater than or equal to 1. So we write out the statement replacing n with k. That's all we do. So we're assuming that this is true for n equals k. In step 3, we take the assumption that proposition k is true. This is just shorthand for saying that the statement is true for n equals k. Then we want to prove that the statement is true for n equals k plus 1. So, as I explained to you in the previous video, we have to build on this here. Build on what we're assuming to be true. So this here is what we want to prove. So if we're proving that the statement is true for n equals k plus 1, then we have to sum the first k plus 1. We have to get the sum of the squares of the first k plus 1 integers. And if we're going to use our formula, then we have to replace n with k plus 1. So let's look at the formula again. So we have to replace n with k plus 1. And we get k plus 1 times k plus 1 plus 1, which is k plus 2, times 2 times k plus 1 plus 1. That's 2k plus 2 plus 1, or 2k plus 3. So we should get this here. We just replace n with k plus 1. N and this with k plus 1. So this thing is what we're trying to prove. So in order to prove this, we have to build on our assumption statement, which is this here. So we have to somehow go from this to this. Well, you can see what to do on the left hand side. We just add on k plus 1 squared. We just add that to the left hand side. But if we add it to the left hand side, we must add it to the right hand side. So remember, everything in blue is what we're trying to prove. So here is our assumption statement. So I've added k plus 1 squared to both sides. So k plus 1 squared added to the left hand side and k plus 1 squared added to the right hand side. So you can see that the left hand side of this now is equal to the left hand side of what we're trying to prove. So it remains for us to prove that the right hand sides are the same. So we have to prove that this here equals this here, and then we're done. So now I've written this thing over here. Notice that we can write k plus 1 squared as 6 times k plus 1 squared over 6, just to get a common denominator. Notice also that we can factorize this k plus 1 out of the numerator. So we're going to be adding the numerators of these fractions because the denominators are the same. They're both 6. So if we factorize out that k plus 1, what are we left with? Well, we're left with k times 2k plus 1 plus 6 times k plus 1. Okay, so I factorized out k plus 1 from this numerator, and I factorized it out from this numerator as well. So for this numerator, we will be left with 6 times k plus 1. Now, let's look at what's inside the square brackets. So we have 2k squared plus k plus 6k plus 1. That's 2k squared plus 7k plus 1. Now 2k squared plus 7k plus 1 can be factorized into k plus 2 by 2k plus 3. So you can see now that this is indeed equal to what we're trying to prove. So by adding the same thing onto both sides of our assumption statement, in other words adding k plus 1 squared onto both sides of our assumption statement, we end up proving that the statement is true for n equals k plus 1. So if it's true for n equals k, it's true for n equals k plus 1. Now the logic of induction kicks in. If you haven't seen the previous video, I'll just remind you. So in step 1, we show that our statement is true for n equals 1. In the last two steps, steps 2 and 3, we show that in step 3 we show that if the statement is true for n equals k, where k is any positive integer greater than or equal to 1, then it's true for n equals k plus 1. So in particular, if our statement is true for n equals 1, then it must be true for n equals 1 plus 1, which is 2. So if it's true for n equals 1, it's true for n equals 2. But we know it's true for n equals 1. We show that at the start, so it must be true for n equals 2. And we can continue like that. If it's true for n equals 2, which we've just shown it is, then it's true for n equals 2 plus 1, which is 3, and so on. So our statement is true for all natural numbers.